Hello, today we will continue with chapter 4 on crystal vibrations. In particular, we will review what we did last time. That is, if I have a lattice with a diatomic basis. So we agreed that if we have a lattice with two different atoms as bases, one of mass m1, the other with mass m2, that in order to find the dispersion equation, that is omega as a function of k, we have to write Newton's second law in terms of us and vs and the spring constant c. Okay, we took that the springs are all identical with a spring constant c, and we got these two equations. And in order to get omega as a function of k, we said that we have to get the determinant of these two equations. And we found that there will be two solutions. One, we called it omega plus, and the other, we called it omega minus. The first one, we said it is the optical branch, that is the optical mode. In this mode, the atoms vibrate against each other, okay? But their center of mass is fixed. If the atoms carry opposite charges, we may excite a motion of this type with the electric field of a light wave, so that this branch is called the optical branch. That's why it's called the optical branch. The second branch, the omega minus branch, it's the acoustical branch, and the atoms, in this case, the atoms and their center of mass, they move together as in long wavelength acoustical vibrations. That's why it's called the acoustical branch. At the Brillouin zone, that is at k equal minus pi over a, at k equal plus pi over a, we found that omega plus will be square root of 2c over m2. Omega minus is square root of 2c over m1. So these were the results from last time. We found what happens at the long wavelength regime. So here, for example, 1Ka is almost 0. We found that omega would be around 2c into 1 over m1 plus 1 over m2. And over here, it's linear, just like the case of one basis atoms. Okay, now we will solve exercises on with these ideas. For the problem treated in section 3, section 3 is this section over here. Okay, so vibrations of crystals with diatomic bases. This is section 3. Find the amplitude ratios U over V for the two branches at K maximum equal pi over A. So the question is to find what is U over V. 1, K equal K maximum equal pi over A. Just as simple as this. We have to show that at this value of K, the two lattices act as if decoupled. So here we will go directly to what we got as the solution. So we got actually that m1 omega square minus 2cu plus c into 1 plus e minus ikav equal to 0. And this is the other equation. So these are the two equations which are here. Okay, these are our two equations. But we will put, instead of k, pi over a. So if we put here pi over a, I will get e to the minus I pi. And here I will get e to the I pi. And what is e to the I pi? It's nothing but minus 1. So I will get here e to the minus ika is e minus I pi. So this is minus 1. E to the ika is also minus 1. Now if I put from the first equation u over v, it is c into 0, okay, to 0, divided by this thing here, m1 omega square minus 2c. So this is 0. Which means u is 0 for any value of v. And in the second equation, if I put v over u, that is, I take this term to the other side, and then I take v over u, it will be c into 1 plus e to the ika, which is again 1 minus 1, so it's again 0. So v is 0 for all values of u. So indeed, for k equal pi over a, the two lattices act as decoupled. Decoupled means they are not dependent on each other. For any value of v, u is 0. Here, for any value of v, for any value of u, v is 0. They are decoupled. They are not related to each other. Okay, this is only happening at pi over a and periodically after that. because apart from that, here U and V are coupled. They depend on each other. But when K is pi over A, they are not dependent on each other. So they are decoupled. Okay, so this is the first question. Then consider the normal modes of a linear chain in which the force constants between nearest neighbors atoms are alternately C and 10C. So this is again a diatomic chain, but a bit different from the one we worked in last lecture, because in last lecture we took that the C is constant, is the same, okay? Now we are saying that one of them is C, the other one is 10C, but let the masses be equal. So we don't have M1 and M2, we have M. Okay, so now we C and 10C, but we have M1 equal M2 equal M. I will simply go back to the original equations and derive everything, but instead of M1, M2, I will be putting M. Okay, and we need to solve this. Let the nearest neighbor separation be A over 2 and find omega of K at K equals 0 and at K equal pi over A. And sketch the dispersion relation by I. That is, you don't have to sketch it exactly the same. Just put what is omega at K equals 0, what is at K equal pi over A, and just sketch it by I. Okay, so we will simply start with the same equation. So here now I have US minus 1, VS minus 1, US, VS, US plus 1, US plus 1, S plus 1. And this is C1, this is C2, okay, because they are now different. So if I write the equations, it's exactly the same. I will start with mv2 US by dt squared equals C1 into VS minus US, right? Because this is here C1. Then minus C2 into US minus VS minus 1. Same thing for d2 VS by dt squared. Then we say let US equal to this thing, let VS equal to this thing. So exactly as before. If this is US, then US plus 1 is this, okay, which is e to the I KSA, e to the I KA. This is nothing but e to the I KS plus 1A. Okay, e to the minus I omega t. First derivative will be minus I omega. The rest of the equation, d2 US by dt squared is minus omega squared u e to the I KSA e to the minus I omega t. VS plus 1 treated in the same way. We will say it is V e to the I KSA e to the I KA e to the minus I omega t. The first derivative of that as a function of t is e to the minus I omega V I KSA e to the minus I omega t. And the second derivative is minus omega squared u e to the I KSA e to the minus I omega t. And then I go back to my equation and I take common e to the I KSA e to the minus I omega t. So by taking that in common, I can simply delete it from the whole equation. These are two equations actually. And then I will have minus m omega squared u is C1 into V minus u minus C2 u minus V e to the minus I KA minus m omega squared V equals C2 into u e to the I KA minus V minus C1 into V minus u. And I take u common, and I will have minus m omega squared plus C1 plus C2 minus V common into C1 plus C2 e to the minus I KA. And this is the second equation. And I just write them a little bit differently here. That is by putting the u on the other side and v on the other side. And then I have to get the determinant. So these are the equations 3 and 4. And in order to find the solution, I have to find the determinant here. And even before that, the determinant, by just putting that at k equal to 0, what happens at k equal to 0 is that I will get, this is minus C1 plus C2. So I will get minus m omega squared plus C1 plus C2u is minus C1 plus C2v. And the other one will be minus C2 plus C1u plus minus m omega squared plus C1 plus C2v is equal to 0. But C1 equals C, C2 equals 10C. So I just plug them in this. And then I get the determinant to be equal to 0. And I solve these two equations. So the determinant, I just get this times this minus this times this, okay, equal to 0. So I will get the solution, two solutions, omega equal to 0 and omega is equal square root of 22 22c over m. Okay, so these are the two solutions at k equal to 0. Now I have to repeat at k equal pi over a. So I go back to at k equal pi over a, that is ka is equal to pi. So e to the ika is -1 and e to the minus ika is equal to -1. Now I go back to equation 3 and 4. They will give me minus m omega squared plus 11cu minus c minus 10cu equal to 0. Minus into minus 10c plus cu plus minus m omega squared plus 11cv is equal to 0. Again, minus m, I'm gonna write this, I'll do a little bit more of math. Here I have c minus 10c, so that is minus 9c. With a minus outside, becomes plus 9c. And here I will also get 9c. And then I do the determinant, and I work the determinant of this. And I will get minus m omega squared plus 11c squared minus 81c squared equal to 0. And I will get two solutions. Omega equals square root 2c over m, and omega equals square root 20c over m. So what did I get here? I got that at k is equal to 0, I have 0 and the square root of the 22c over m. This is from the at k equal to 0. And at k equal pi over a, I got the two solutions, square root 2c over m and square root 20c over m. And then I sketch it by eye. Okay, I don't have to make it perfect. So we know that from down it is something like this, and from up it is something like this. It should look like what we saw over here up. Okay, so this branch should be like this, and this branch should be like this. And this is how we sketch it here by eye. Okay, so this is the end of today's lecture. As usual, if you have any questions, just send me an email and we try to have a live session where I will answer your questions. Bye-bye.